Hi everybody, and welcome to our acid and base notes part 2. If you recall from our last notes, we reviewed naming and just being able to identify strong and weak acids. Today we're going to talk about several things. If you do want to pause, you will need your calculators today. You're going to need a real scientific or graphing calculator today, so please make sure that you have that. All right, so let's just start by talking about some general properties of acids and bases. All right, so first off, acids, as far as general properties, tend to taste sour. Not that we really encourage you to taste chemicals all of the time, but we are actually very accustomed to eating and drinking very acidic food. Things like lemons, all right, those are acidic. All right, acids can be either strong or weak electrolytes. When we talk about something being an electrolyte, we mean its ability to dissolve in water. A strong electrolyte will dissolve completely in water and give off ions, whereas a weak one only dissolves a little bit. And we're going to talk a lot more about that as we go on. All right, bases. Okay. Bases tend to have a bitter taste and feel slippery. As far as a base goes that we are accustomed to, soap is kind of the classic example of a base, and we know that kind of slippery feel. Again, they can be strong or weak electrolytes, and we're going to talk quite a bit more about that in a future set of notes. All right, so as far as defining acids and bases, there's two definitions that we need to be familiar with. The first is known as the Arrhenius definition. All right, an Arrhenius acid is a hydrogen-containing compound that will ionize to give you hydrogen ions in water. So for example, hydrochloric acid, HCl. If I were to put this in water, it's going to give you hydrogen ions and chloride ions. Great. All right. And that's exactly what hydrochloric acid does when I put it into water. Okay. An Arrhenius base is a compound that will ionize to give off hydroxide ions in water, something like sodium hydroxide. All right. I put that into water and it's going to give me sodium ions and hydroxide ions. Fantastic. All right. This definition is excellent and it works very well, particularly with strong bases. It is, however, a little limiting because we do have certain cases where we have a base that doesn't have hydroxides. All right. Acids will always have hydrogens. So the acidic definition is great. Bases, however, don't always have hydroxides in them, which leads us to our next definition, which is known as the Bronsted-Lowry definition. All right, and this is a much more broad definition than the Arrhenius one. Under Bronsted-Lowry, an acid is defined as a hydrogen ion donor. Remember, a hydrogen ion is just H+, so it's a hydrogen ion donor. It's going to give it away. Whereas a base is a hydrogen ion acceptor. So this broadens our definition of bases. So let's see where this is going to come into play. All right, so here's our example of ammonia. Ammonia, NH3, we're familiar with this. We've dealt with this one a lot. All right, and ammonia is a classic, what we call weak base. We see it all of the time. And let's see what I mean by an ion donor and an ion acceptor. All right, so let's look to see what happened with this ammonia. NH3 on the left side of my equation, and then all of a sudden it's NH4 plus on the right side. So what happened is this NH3 actually accepted a hydrogen, which makes it a base. Where did it get that hydrogen from? Well, let's look at this water. What happened? It's H2O on the left, and it's OH minus on the right. The water gave off a hydrogen, which makes it fall under the category of an acid. Now, what's going on over on the right? If you notice, all right, the ammonia gained that hydrogen and it became ammonium ion. And we actually call this the conjugate acid. And I'll just abbreviate that CA under ammonium. And that is the particle formed when a base gains a hydrogen ion. So again, let's take a look at this. NH3 gained a hydrogen. Because it gained a hydrogen, we call it a base. But after it gained that hydrogen, we call it the conjugate acid. So the base becomes the conjugate acid, and the acid becomes the conjugate base. All right, the particle that remains after the acid has donated the hydrogen ion. So I had water here, and water gave the hydrogen away. What's left over is the conjugate base, which happens to be the hydroxide ion. All right, let's look at another example right here with hydrochloric acid. All right, so HCl, looking from left to right, what happened to it? It donated the hydrogen, and we know that that's an acid anyway. It's hydrochloric acid, so that helps us. So it's an acid. Remember, whatever happens to the acid becomes the conjugate base. All right. Also, keep in mind, even when we call something a conjugate acid, it still has to have a hydrogen. So there's no way Cl- could have been any type of acid. So that kind of helps you figure it out as well. Then we have the water here. Well, what happened to the water? The water gained a hydrogen from the left to the right. If you gain hydrogens, you are considered a base. And then this H3O plus is our conjugate acid. H3O plus is called the hydronium ion. And we're going to see that quite a bit in this unit, that hydronium ion. Okay. As you can see from the above examples, okay, water can be a hydrogen ion acceptor or a donor. All right, up here we had water being the acid, and here water is the base. All right, water, because it can act as an acid or a base, is called an amphoteric substance. Okay, so again, an amphoteric substance means it can be an acid or a base, just depending on the situation. Also, to go back and just talk a little bit of terminology with you, when we talk about a hydrogen ion, it's the same thing as talking about a proton. Remember, most hydrogen atoms don't have neutrons, all right? And so when we're talking about H+, it means it's lost its electron, and all that's left for little hydrogen there is just a proton. So you may see on some practice sheets and things like that, them talking about proton acceptors or proton donors. It's the same thing as a hydrogen ion. All right, so it's time to deal with a little bit of math, all right? And we are going to talk about what happens when water actually dissolves in water, which seems a little funny, all right? So almost any substance will ionize slightly in water. Even water breaks up a little bit in water, and we call this auto-ionization. All right, so it's actually impossible to have 100% pure water. What's going to happen instead, okay, is you get, and you can kind of imagine, it's a little bit easier if you'd like to imagine two waters. All right, and it ends up giving you a little H3O plus hydroxide ion. So that just occurs in water all of the time. Now, please realize there's a shorter way of writing this, and we write it as this, H2O, all right, back and forth with H plus and OH minus like that, okay? So you will get a little of this auto-ionization at any temperature for water. Now, that's not to say you're gonna get a lot of hydrogen ion and hydroxide ion. At 25 degrees Celsius, all right, the concentration of the hydrogen ion is 1 × 10⁻⁷ molar. So it's not a whole lot. All right. Now, why we consider water a neutral substance is because the hydrogen ion will equal the hydroxide ion. So it's not like we have an overabundance of either one of them. They are going to be equal when we are talking about pure H2O. All right. So since the concentrations of hydrogen ion and hydroxide ion are equal, we say that pure water is a neutral substance. All right, so what we're going to talk about is something called the ion product constant for water. And this is known as Kw. So we're bringing back this concept of equilibrium. All right, and for Kw is the hydrogen ion times the hydroxide ion. Now, I've already told you that at 25 degrees, and we're going to stay at 25 degrees Celsius the whole time, so we don't need to worry about this changing. Hydrogen ion is 1 times 10 to the negative 7th. Hydroxide ion is 1 times 10 to the negative 7th. And that's going to give you 1 times 10 to the negative 14th. All right, this is going to be an equation that we are going to use later. So please keep this in mind. Okay, so we can use this equation when we add something else to this pure water. So what happens when you add something else to water? Well, when an acid is added to water, all right, it gives off hydrogen ions, okay? And it becomes an acidic solution. So an acidic solution is one in which the hydrogen ion is greater than the hydroxide ion. If you add something that gives off hydroxide ion, all right, or a basic solution, this is also known as an alkaline solution, okay? This is one where the hydroxide ion is greater. So let's take a look at an example and to see where we can use Kw for this example. What is the hydroxide ion concentration in a solution that is 3.5 times 10 to the negative 3rd molar hydrogen ion? This is a solution in which an acidic substance has been added. So remember, Kw again is the concentration of hydrogen times the concentration of hydroxide. We know that Kw is always 1 times 10 to the negative 14th. It is a constant. All right. So that's going to be equal to, we know the hydrogen ion concentration, 3.5 times 10 to the negative 3rd. All right. And what we're looking for is that hydroxide ion. All right. So we want to know what that's going to be. Well, we're just simply going to use our calculators, take a moment, solve for hydroxide. We're just going to divide each side by 3.5 times 10 to the negative 3rd. Make sure that you are comfortable putting these into your calculator. And you should get for this, all right, 2.8 times 10 to the negative 12th molar. All right, again, we're just going to go 1 second E, negative 14, and divide that. I like to use parentheses in the bottom, 3.5, second E, negative 3. And that gives us about 2.8. If you rounded that to 2.9, that's totally fine, times 10 to the negative 12th. Okay, all right, that actually should be 2.9. Yep, so we'll go 2.9 times 10 to the negative 12th. Okay, great. All right, so you can pause right now and do these two on your own. Okay, and we will take a look. All right, what is the hydrogen ion concentration if this is your hydroxide? So again, remember 1 times 10 to the negative 14th is equal to the hydrogen ion, which is what we're looking for, times, and you can leave this in brackets if you like that, 4.9 times 10 to the negative 11th. So you end up getting, and again, please practice putting these into your calculator. It is always a big help, and this is about 2.0 times 10 to the negative 4th molar as your final answer there. All right, and then finally, again, same idea. And what is your hydrogen ion concentration? Again, times 3.6 times 10 to the negative 2. And your hydrogen ion is about 2.8 times 10 to the negative 13th molar. So nice and straightforward. We're just kind of doing some nice, easy calculations there. This is going to lead us to being able to talk about the pH scale. And this is something that we're all familiar with from kind of elementary school science. All right. The pH scale is a scale that was actually developed to allow people, non-scientists truly, to be able to talk about how acidic and how basic certain substances are. The pH scale is a logarithmic scale, and remember, we use logarithmic scales when we're dealing with very large, or in this case, very small numbers. Because it is a logarithmic scale, please remember a change is very drastic. So if we say something has a pH of 6 and then something else has a pH of 5, that's not a little change, it's actually a huge change. All right. In chemistry, wherever you see this lowercase p as in pH, you want to think mathematically negative logarithm. So pH, and this is really important, I'm going to star this, pH, always a lowercase p by the way, is the negative log of the hydrogen ion concentration. Why is it negative? Most values for hydrogen ion concentration are going to be very small. They're going to be numbers less than 1. They'll be decimals. And because of that, we do a negative log, so we get a scale for our substances that give us a nice positive number. Again, this is supposed to be very user-friendly. The pH of water, remember the hydrogen ion concentration in pure water is 1 times 10 to the negative 7th. So the pH of that is 7. All right. Orange juice has a hydrogen ion about 1 times 10 to the negative 3rd. That gives us a pH of 3. All right. Household detergent is about a pH of a pH of 10, hydrogen ion concentration of 1 times 10 to the negative 10th. All right. Okay. When we deal with much stronger acids, such as hydrochloric acid and a high concentration of that, like let's say 10 molar, the pH would actually be negative. But that doesn't come up a lot because, again, pH is typically used for things that are commonplace, that people would typically deal with, or in biological systems where we don't get very strong extremes of acidity going on. All right, so let's do some practice with this pH, and really this practice is going to take place in your calculator. So if I tell you that you have a hydrogen ion concentration of 4.2 times 10 to the negative 8th, all we do, and hopefully you can see the calculator, but I'll talk you through as well, negative log, that's what the P stands for in pH, and then you just simply 4.2 second EE negative 8, and that gives me a pH about, you want to go to the hundredths place with pH. So 7.38. So this would be 7.38. All right, great. That would be the pH. All right, so now what is the pH of a solution? Now I'm giving you the hydroxide ion concentration. Now remember, pH is the hydrogen ion. So what we can do is we can use kW, just like our problems before. Remember, 1 times 10 to the negative 14th is going to equal your hydrogen ion times 6.4 times 10 to the negative 3rd, because that's your hydroxide. When we do this, we get a hydrogen ion of 1.56 times 10 to the negative 12th. We're going to go ahead and I'll clear my calculator, negative log 1.56 second EE negative 12. All right, and that gives me a pH of 11.81 for that one. Okay, great. Now, as we can see, okay, pHs are going to range. They can be negative numbers, but we more think of them as kind of ranging from 0 to 14, where 7 is in the middle, that is neutral. Below 7 means we have an acidic solution, and above 7 means we have a basic solution. Now, there is a nice little shortcut that is going to allow us to solve for pH a little bit quicker. And to do that, we deal with what is also known as POH. Remember, the P stands for negative log, so POH is the negative log of the hydroxide ion concentration. All right, and here's this nice little shortcut. pH plus POH will always give us 14. So if you know that you have a pH of let's say 5, and you want to know what the POH is, you're just going to go 14 minus 5. So that would be 9. Okay. So let's go over the different ways that we can solve these problems. Okay. So we have 4 different types of pH problems we're going to go over to finish out the notes today. Again, you need your calculator. All right, so the first one is calculating pH from hydrogen ion. We already did that. Remember, that is the negative log of the hydrogen ion concentration. Nice and straightforward. Then we need to be able to find, go in the other direction. So let's take a look. The pH of an unknown solution is 5.25. What is the hydrogen ion concentration? All right, so to do this, there's really not anything to write. All right, it is simply calculator work. To do this, we're going to take the anti-log of the negative pH. So to do that, you are going to hit second log negative, whatever that pH is, 5.25. And that is going to give you 5.62 times 10 to the negative 6th molar hydrogen ion. All right, let's talk through that one more time. This is your pH. To find the hydrogen ion concentration, all right, so H plus concentration, you're going to hit the second function, log, then hit negative, then punch that number in, 5.25. All right, then that's going to give you the concentration. Okay, nice and straightforward, but you do have to keep that in mind. All right, then we're going to go to our third type of calculation, finding pH from POH. All right, so there's a couple different ways of playing with this and doing this. All right, so what is the pH of a solution that has a hydroxide ion concentration of 2.2 times 10 to the negative 4th? Well, there's a couple ways for you to do this. I think the fastest way is finding the POH and then finding the pH. You could also use KW. Either way is totally fine. So I'm simply going to find the POH really quickly because you're going to do the same thing that we did in the last problem. This is the hydroxide ion concentration right there. So I'm going to go second log negative. No, I'm sorry, excuse me. That's the hydroxide ion concentration. So I'm just going to find the POH, which is the negative log. I'm sorry about making that mistake. 2.2 second E negative 4. And that's going to give me the POH of 3.66. Right? Again, if I'm giving you the concentration, you just simply take the negative log of that number. All right, so we just did, so that's your hydroxide ion. We're just going to take the negative log of 2.2 times 10 to the negative 4th, and that gives us 3.66. I'm then going to go 14 minus 3.66, and 14 minus 3.66 gives me 10.34. And that is your pH. Nice and simple. All right, fantastic. All right, finally, we're going to do one that has everything. So what is the pH, POH, and hydroxide ion concentration of a solution with a hydrogen ion concentration of 3.3 times 10 to the negative 8th? Is this an acidic or a basic solution? So again, this is really going to be all calculator work. It really depends on how you want to do it as far as the order. I'm going to go ahead and quickly find the pH. So I'm going to just do the negative log. Where's my negative log of 3.3. Okay, second E, negative 8. And that gives me 7.48. 7.48 is my pH. All right, I'm now going to find my POH by simply going 14 minus 7.48. And so my POH is 6.52. All right, then finally, I am going to go second log negative 6.52. And that gives me about 3.02 times 10 to the negative 7th, and that is my hydroxide ion. And that is 3.02 times 10 to the negative 7th molar. All right, so as you can see, this is a lot of calculator work, so you need to have that calculator ready, and we're going to be doing a lot of practice with this as we go on. All right. Hopefully everybody has a great day. Take care.